we have understood that because of small size of obstacles or small openings, I could have bending of light, and that is known as diffraction. So I'll just write that thing for you because that's a new thing. Diffraction. And what exactly is this? This can be said as bending of light due to small obstacles or small openings. So if I have small openings and obstacles, by small I mean comparable to the wavelength of light, I'll observe a bending of rays of light. And why would that happen? That would essentially happen because this wavelength is kind of an impediment to the motion of light. Why? If the obstruction was of a large value, so a disturbance won't have found out a way out. But if the obstruction is of a small value, what can happen is it could bend and produce a different sort of a wavefront out of that obstruction, and that produces diffraction, because now the same wavefront is modified because of the small opening. So let's study this diffraction. Now, diffraction is generally studied by using a very small opening known as grating. This here is your grating. There's small, exaggerated small opening. I have just tried to exaggerate it for you to understand this. This is grating. This sometimes known as diffraction grating too. Diffraction grating. And there's a source here, S0. This would emit out spherical wave fronts. The moment it reaches over here, the spherical wave front changes its shape. And ideally, if light was not a wave, it should have traveled along this line and there should be shadow across these positions. But there are no shadows across these positions. Light also reaches here and here, which means light bends around here, right? So if we have a screen over here, known as S. S0 is the source, this is diffraction grating, and this is my screen. So I can observe a pattern of bright and dark areas, similar to the interference thing which you had seen. But this is not interference. We'll come to it, why it is not interference, it's different than that. But let's understand that I had a source, I let it pass through a small opening, diffraction grating, and what I observed was bright and dark areas in a screen. And if the light was not a wave, there should be just a shadow over here. Rather, there should be shadow over these positions. I don't have shadow over these positions. I have light over here and also here in these sides. That's diffraction for you. And diffraction are of two types based on the scientists which covered them or did research in them. One is your Fraunhofer and the other is Fresnel. What Fraunhofer did was, he said that if my source is at infinity and screen is also at infinity from grating, then I'll have all the rays almost parallel to the grating, right? Because if rays are coming from infinity, they would be parallel. And from diffraction grating to screen also they would be parallel because this is infinite distance away from me. Now, how to achieve this? I cannot reach infinity. So what I do is, I put a converging lens here and put the source and screen at their focal planes. The moment you put source and screen at the focal planes of the converging lens, respective converging lens, you'll see that your task is done because all the rays from this screen on the converging lens, and then they would become parallel because this is focal plane, and this rays, when they reach the convex lens, they would again converge and converge to your focal plane of the screen. So practically I have parallel rays. So practically I have parallel rays from grating to screen. That has been achieved by a smart usage of converging lens on both the sides. Now, what is Fresnel diffraction? In Fresnel diffraction, I don't have to do such laborious task of putting converging lens. A normal setup would do. In the normal course of study, we won't be discussing Fresnel diffraction. We'll be discussing Fraunhofer diffraction, right? So what exactly is Fraunhofer diffraction? We'll study single slit Fraunhofer diffraction. Single slit. See, it's slightly different than your double slit experiment, right? Even the name of it is different. Single slit Fraunhofer diffraction. How does it happen? Very simple and elegant process. You keep a slit here of some B dimension. This slit is of B dimension. Small slit. And I have put a converging lens over here. To achieve parallel rays on screen. There's a converging lens here too, which I don't need to use because that's very understood. This is your screen. Now, if my rays are parallel to this converging lens, then they would all converge to the central point. It would be a maxima. But let's say they're not converging at the central point. And why that would happen? If let's say I'm talking of the rays starting with some angle theta, right? Even this ray, theta, even this ray, theta. What would happen is, after convergence, they would meet at one point P. This was your central point O. Now, if you join this, as this is perpendicular to all the rays, right, what you can say is, in this triangle, if this is theta, even this is theta, I'll draw this for you. This is B, this is theta. Now, if you are careful enough, you'll understand that this guy is producing the phase difference, because rest all is the same wave which is going. There's no path lag, there's no path difference lag. So this delta over here is your phase difference between this and this point, or rather these two secondary sources of the same wavefront. How would I calculate delta? Very easy. Delta by B is equal to sine theta. So delta is equal to B sine theta. Now, if I were to calculate delta for this smaller triangle, this one now, then this would become B by 2. So the smaller would have B sine theta by 2, or B by 2 sine theta. And why is this relevant for our case? This is relevant for our case because if I think of any point on this half, there would be a corresponding point b by 2 below. Take any point here on the first half. There would be a corresponding point b by 2 below, and they would reach here traveling a phase difference of b by 2 sine theta. And if this is equal to lambda by 2, then I'll have a minima, right? So if all the points are suffering the same fate, then I'll have a minima. So b sine theta is equal to lambda becomes the minima, first minima. Similarly, if I do the same idea, same logic, I have divided this into two halves. Now if I divide them into further more halves, what I will see is there would be n coming here, right? So for all integer values of n, I'll get a minima. This is the condition for minima. Condition for whenever I say minima, minima means a dark fringe or a dark area. So central was the maxima, this was the minimum.